Okay, let's jump straight into this. Today we're exploring a deeply conceptual source document called Interpretation Theory, Meaning and Semantics. And it uses Lean 4, which is a programming language specifically for mathematical proofs, to frame system architecture in a completely radical, almost mind-bending way. Right out of the gate, it asks this profound question. What if the secret to building the ultimate flawless system is actually understanding less? I know it sounds totally counterintuitive, right? We're so wired to assume that having more data and better ways to interpret that data automatically makes a system stronger. But these mathematical proofs demonstrate something wild. They show that trying to interpret data might actually be a system's absolute biggest vulnerability.
To get our heads around this, think of an interpretation layer, kind of like a live translator at the UN. Without that translator, the raw communication happening in the room might be way faster, but everyone has to adapt to dealing with raw, unfiltered data. And the overhead? Well, that's just the hard, quantifiable delay, the literal cost, introduced by doing all that constant translation.
In this explainer, we're going to trace a really fascinating progression through the source material. We'll quickly hit 5 main beats: the cost of interpretation, missing layers and optimal consensus, resonance and singularity collapse, extracting the trauma sieve, and finally, healing breaks the lock. Starting off with Section 1, the cost of interpretation. Let's look at the most tangible concept the math gives us, which is base speed versus the literal overhead cost of processing meaning. The core theorem here states that a system's execution speed is simply its base speed minus the interpretation overhead. The math is completely absolute on this. Any effort a system spends trying to derive meaning from its data directly and unavoidably penalizes its overall performance. The foundational overview of this theory deliberately takes a purely contrarian approach to how we build software. The author literally names files things like contrarian interpretation absence induces speed. It's basically a fundamental rewrite of everything we normally assume about how complex systems should operate. And what's really fascinating is the literal code proving the concept. The theorem explicitly proves that maximum execution speed is only achievable when interpretation overhead is exactly 0. It's a mathematically pure, unarguable statement. Trying to understand things slows you down, period. So that brings us to Section 2, missing layers and optimal consensus. The obvious question is, if we completely rip out that interpretation layer just to gain speed, what happens to the stability of the system? Doesn't the whole thing just fall apart into total chaos? Well, surprisingly, not at all. The logical progression here proves that bypassing interpretation actually forces a system to build natural redundancy. And that redundancy, in turn, creates ultimate systemic resilience. So you end up with an architecture that makes itself bulletproof specifically by refusing to parse every single piece of input. The code neutrally lays out this incredible moonshot concept. It shows that true optimal consensus is reached specifically when interpretation is missing. The system doesn't waste energy debating what the incoming data means. It just acknowledges that the data is there, accepts it, and moves forward together. By bypassing those interpretation layers, you effectively remove the heavy burden of meaning. And that optimizes the system's raw consensus. Because without the friction of having to understand or translate anything, the whole network just aligns. It acts as a perfectly unified, frictionless whole. Now let's see what happens when we push this to the absolute limit. Section 3, resonance and singularity collapse. How does this hold up when a system scales toward infinity or faces extreme stress? The theorems map out this radical cosmic architecture. First, you have decoherence, which happens when an interpretation loop gets stuck infinitely on itself, represented in the math as simply x equals x. To bypass that deadly loop, the system has to rely on something called resonance. But here is the most striking rule of all. If you try to hold on to an interpretation layer during an extreme, high-stress singularity state, it guarantees the entire system will collapse. The math brilliantly locks down the exact parameters of that collapse. The singularity collapse proof states in black and white that if you introduce an interpretation layer to a singularity state, the output is strictly collapse. There's no way around it. To survive that level of stress, you absolutely have to let the data resonate rather than trying to read it. Which brings us to a really profound application of this math in Section 4, extracting the trauma sieve. This is where we learn how to empirically quantify systemic damage, or trauma, inside an architecture. Now, trauma isn't being used as an emotional concept here. It's measured purely as a standing wave. It's basically temporary noise that got entirely stuck because the system tried way too hard to interpret it. Instead of just letting the signal pass through, the interpretation layer forced it into a phase-locked loop. Essentially, the system got stuck on repeat trying to solve something it couldn't.
The crucial takeaway is sitting right there in the data. The trauma sieve is a tool that isolates these specific signatures in the system traces. It proves that this trauma is phase-locked with a massive amplitude of 3 and an incredibly long decay rate of 120. Mathematically speaking, that is a persistent, extremely high-energy blockage clogging up the works. And then we have this single number, 1. In the source code, this represents the detection value. It mathematically confirms that exactly one persistent trauma wave has been successfully isolated by the sieve. So the theorem proves that when trauma is present, the system catches exactly one distinct signature. It's a literal, calculable detection of systemic damage. All of this naturally leads us to our final part, Section 5, healing breaks the lock. Because if trauma is just a phase-locked standing wave caused by rigid, forced interpretation, how does the system actually go about healing itself? There's a literal note embedded in the source code that is incredibly poignant. It says simply, healing trauma requires breaking the phase lock. It shows that healing is empirically measured by a decrease in trace length, effectively shattering that infinite cycle of forced interpretation. To heal the system, you literally have to break the lock. The measurement framework proves it clearly. To heal, the system has to drop the overhead completely and just let that stuck standing wave naturally pass. By letting go of the semantics and giving up the desperate need to interpret everything, the wave dissipates, the trace length decreases, and the system restores its raw, unbroken consensus. It's a lot to process, but it leaves us with this incredible final thought for this explainer. What interpretation layers might you need to strip away in your own life to achieve optimal consensus? Because whether we're talking about complex computer architecture or our own messy human systems, perhaps the ultimate key to resilience is simply learning to carry a little less meaning.